the output of this function to result. So this, yeah, this is a great question here. So what happens if we run this again? Here, we'll take this out here for a second. Run it again. So it printed 5, but now what's in result? Nothing, right? So you need return in order to send your output into, like if you're going to assign the output of a function to a variable. Print doesn't do that. Print just displays it on your screen. Return actually gives you function output. Does that make sense? All right, let's move on to the, let's put some of this into practice. We're going to move on to our in-class activity. We're going to have practice building a function to do something interesting with genomic data. And I want to give you a brief introduction to what we're going to do here. All right, so what I want you to do is, so there was this paper published recently that proposed a new way of detecting transcription factor binding sites. Okay, so what the group did was, so normally the way you detect transcription factor binding sites is you have your stretch of DNA, right? You've all heard of Cheq-seq. You have a transcription factor binds to DNA. So normally what happens in Cheq-seq is you use formaldehyde to cross-link your DNA to the protein. You then shear up the DNA. You can use an antibody to pull down that transcription factor, and then you reverse the cross-links and you sequence the DNA. So that's sort of the standard method for identifying transcription factor binding sites on a genomic scale. Cheq-seq is what this new method is called. It uses a slightly different approach. And the authors argue that it has some advantages. Okay, so again we have our DNA. What happens in Cheq-seq is you have your transcription factor, and instead of cross-linking your proteins to the DNA, they're actually expressing a transcription factor that's fused to a micrococcal nuclease, we'll call it MAH. And in the presence of calcium, this will cleave the DNA around the binding site. So you'll start, you'll get these fragments here, other fragments there, and so then you detect where the cleavages happen by sequencing, and you can do it without any sort of cross-linking and the artifacts that might be induced by cross-linking. So one nice advantage of this approach that the authors argue is an improvement over Cheq-seq is that you can get data over time. You can get kinetic data. So you can let this MAH digestion go for 10 seconds, stop the reaction, harvest the DNA, see what you get. You can let it go for several minutes and see what you get. Any questions about this? I know it's a brief summary of the method, but it's basically the idea. It's a new method for looking at, for identifying transcription factor binding sites. So I'm just going to show you one figure from the paper. The authors argue is, let's see if we can zoom this in here. One of the big claims that came out of this, what the authors make in this paper is that they discovered a new class of transcription factor binding site, they argue. They argue that there are sites that show up very quickly after this reaction is proceeded after only a few seconds, that they call fast binding sites or fast peaks. And then there are other sites that show up only after digestion for several minutes. So I'm just going to dim the lights briefly and show you an example here. We're going to look at this data on the left here. The red shows you when the digestion peaks show up. So here is a clustering diagram of various transcription factor binding sites. So you can see each row here is a different sequence, and then each column is a different time point. So here's a set of peaks where you sort of get your maximum signal after 30 seconds. So these sequences that are in these rows are called fast peaks. And you see another set of peaks that really don't show up until much later in the digestion, in fact 20 minutes out. And these are called slow peaks. And so the authors argue that these represent low affinity transcription factor binding sites. They could reflect a different binding mechanism. If this is actually a real result, it could be quite interesting. I'm going to turn this back on. But there's an alternate hypothesis. So are these slow peaks real, or are they experimental artifacts? So let's go back to our diagram here. So it would be interesting if the peaks were real, if these slow peaks were real, but you can imagine another possibility. So you can imagine your transcription factor with the nuclease, it's bound to DNA. The areas near the binding site are cut rapidly. But you know, over time, the transcription factor maybe binds and unbinds and perhaps diffuses a little bit. And so if you wait long enough, it starts to cut maybe a little more non-specifically along the outside there. And then maybe this is actually the signal that's coming up, and that's what the slow peaks are, right? And maybe they're not real independent binding sites, they're just artifacts of the long digestion. So one way to test this idea, one way to, if you expect this, if this artifact hypothesis is true, where do you expect to find the slow peaks relative to the fast peaks? Is this, what's that?
Adjacent.
Adjacent, right? Either almost on top of them or nearby. Okay. So your task now, I'm going to give you this Cheq-seq data, and your task is to write a function that tests how close, that tells you how close the slow peaks are to the fast peaks. So you're going to get a set of sequence coordinates for the fast peaks, a set of sequence coordinates for the slow peaks, and we can ask, you know, do the slow peaks overlap with the fast peaks? If they do, we wouldn't definitively conclude that they're artifacts, but it would certainly make us more skeptical of them. But if they're not, you know, perhaps we're inclined to think there's something real. All right, any questions so far? I know this is hurrying this along a little bit here. All right, so what I would like to do, I would like to approach this in-class activity a little differently today. I've broken it into smaller chunks compared to other times, smaller tasks. So what I would like you to do is go through one task at a time. When you're finished with the task, put the green post-it on your computer, and when we're done, we'll go over the task. We'll bring everybody up to speed, same level, and then we'll move on to the next task. All right? Good? So, have at it.